Alright, so this is the video on 10.1. Basically, we get introduced to sequences and sums in this section. If you wanted to, you could read a little bit on at the start of 1040, just to get an idea of things. But basically, a sequence is very similar to a function, but it's a function that's domain is a set of positive integers. So basically what that means is instead of being able to plug in, like f of x, we could say what's f of 1.2 or f of 2.5 or whatever, f of pi. In this case, a sequence, we're only going to be able to plug in 1, 2, 3, 4, etc. And sometimes this book starts at 1. A lot of books and computer programming languages and stuff start at 0. So it doesn't necessarily have to be positive integers, but usually it's non-negative integers at the very least. So an infinite sequence is a function whose domain is a set of positive integers. The function values, or terms, of the sequence are represented by a, and then it's got a little subscript, so a1, a2, a3, a4, or a sub 1, a sub 2, a sub 3, whichever you prefer to say. Usually I'll just say a1, a2, etc. Sequences whose domains consist of only the first n positive integers. So if they don't go on forever, then if they terminate, they are called finite sequences. All right, so write the first 4 terms of the sequence whose nth term, or a general term, is given. There's a few names for that. You could say explicit equation. There's a bunch of different ways, but I think we're looking for general term here. So is given. So I'm just going to plug in n equals 1. So I get 2 times 1 plus 5. The next term would be 2 times 2 plus 5. The next term would be 2 times 3 plus 5. And the fourth term would be 2 times 4 plus 5. And so I get 7, 9, 11, 13. Those are the first 4 terms of that sequence. So here, a1 is going to equal negative 1 to the 1 over 2 to the 1 plus 1. Well, that's equal to negative 1 over 3. A2 is going to equal negative 1 squared over 2 squared plus 1, which is equal to 1/5. A3 is going to equal negative 1 to the third over 2 to the third plus 1, which is going to equal 2 to the third is 8 plus 1, it gives me 1/9, and it's going to be negative. And finally, A4 is going to equal negative 1 to the fourth over 2 to the fourth plus 1, which is equal to 1 over 17. So again, you can see it's very similar to a function. It's basically, you can think of this as f of 1, f of 2, f of 3, f of 4. But the thing is about it is there is no 2.5 term or half term or anything like that. It's always going to be whole numbers. So, or in this case, or positive integers for this book. And typically A is probably the most common letter to represent a sequence. We could use any lowercase letter. Typically, uppercase letters are saved for something else that we'll see in a few minutes, but it's not. It's still, you will still sometimes see sequences with uppercase letters as well. But the general convention is a lowercase letter. All right, and then graph of a sequence. Remember how I said they're basically functions where we can only plug in whole numbers or positive integers? Well, if you compare these two graphs, notice they're exactly the same as far as if I just take the integer points on this one, then I've got the graph of the sequence. So it's basically a set of ordered pairs. Recursive formulas. So sequences can also be defined using recursive formulas or recursion formulas. A recursion formula defines the nth term of the sequence as a function of the previous term. A recursive formula also requires a starting point known as this doesn't really matter, but base case. The Fibonacci sequence is defined recursively with 2 base cases. So, in this case, they're using F for Fibonacci, not for F for function. But basically, this is a recursion formula right here. And what that tells me is, remember, this right here is the nth term. This right here is the n minus second term. And f sub n minus 1 is the n minus first term. And what that means is basically to find the third term, if n equals 3, then I'm going to take 3 minus 1, or 3 minus 2 is 1, and then 3 minus 1 is 2. So to find the third term, I'm going to take this first term and the second term and add them together. So if you notice, 1 plus 1 gets me 2. And then if I do 1 plus 2, that gets me 3. If I do 2 plus 3, that gets me 5. And then 3 plus 5 gets me 8. 5 plus 8 gets me 13. 8 plus 13 gets me 21. 21 plus 13 equals 34. 34 plus 21 gets me 55, and so on. That's the Fibonacci sequence. And if you read that page 1040, you'd notice the Fibonacci sequence actually appears quite a bit in nature, in particular like flowers. If you look at the petal arrangements, usually there's the Fibonacci sequence is represented in there. So find the first 4 terms of the sequence in which a1 equals 3 and an equals 2an minus 1 plus 5 for n greater than or equal to 2. Now, these are one of those things where once you get it, they're simple, but sometimes people have a little bit of trouble understanding like the notation, and it just doesn't click right away. So whenever you see a sub n minus 1, I want you to always think of that as the previous term. All right, it's not, so it's a sub n minus 1. It's not n minus 1. It's just a sub n minus 1. So that's just saying to find the next term, take the previous term times 2 plus 5. So a1 is equal to 3. We've already got that. Well, a2 is going to equal 2 times a sub n minus 1. So that's the previous term. So 2 times the previous term. So it's going to be times 3 plus 5, which gets me 11. Now a3 is going to be 2 times the previous term plus 5, which gets me 27. a4 is going to equal 2 times the previous term plus 5, so I get 59. And those are the, so 3, 11, 27, 59 are the first 4 terms of the sequence. So factorial notation. Basically, if I have an exclamation point after a number, that's going to multiply every number, that number times every number below it until we get to 1. So here's kind of, again, if you look at the definition, n factorial is n times n minus 1 times n minus 2 times 3 times 2 times 1, etc. Basically, we're going to just start at the number and multiply it times every number counting down by ones. And then also an important thing to note, might not make sense to you, but when we talk a little bit about counting and probability, it might be able to make a little bit more sense. 0 factorial is defined to be 1. All right, so 0 factorial is 1. All right, so the recursive definition of n factorial is n times n minus 1 factorial. So if I take the, like, 1 factorial is equal to 1, 2 factorial is equal to 2 times 1, 3 factorial is equal to 3 times 2 times 1, which is equal to 6. And if I want to find what 4 factorial is, I could take this previous number here and take it times 4. And I get 24. Because it's 4 times 3 times 2 times 1. And that 3 times 2 times 1, right? That's right there. As you can see on this table on the right side here, these numbers, factorial gets big really quickly. So one of the things, like, again, if you're curious about a huge number, again, 52 factorial is basically the number of ways, a deck could be arranged, a deck of playing cards could be arranged, and you can imagine if 20 factorial is already that big, how big 52 factorial is. Some of you, I might have already told you the story of how you can think of what 52 factorial is. For those of you that I haven't, I'll probably talk about that when we get to the counting video. And then can you find 5 factorial equals 120 using your calculator? You can just go over here, just turn this guy on. 5, math, it's under probability here. Number 4, 5 factorial is 120. All right, so write the first 4 terms of the sequence whose nth term is an equals 20 over n plus 1 factorial. So I'm just going to plug in n equals 1, n equals 2, n equals 3, n equals 4, and go from there. So a1 is equal to 20 over 1 plus 1 factorial. So that's 20 over 2 factorial, which 2 factorial is just 2, so I get 10. a2 is equal to 20 over 2 plus 1 factorial, which is equal to 20 over 3 factorial, which is 20 over 6, which I can divide top and bottom by 2 and get 10/3. a3 is going to be 20 over 3 plus 1 factorial, which is 4 factorial, which is 24. I can divide top and bottom by 4, and I get 5/6. a4, finally, so 20 over 4 plus 1 factorial, which is 20 over 5 factorial, and that's equal to 20 over 120, which is equal to 1/6. So 10, 10/3, 5/6, 1/6. So let's evaluate each of these factorial expressions. Now one thing that's important to do, let's do our calculator for A. I'm going to show you how not to do it. So 14 math prob 4 divided by 2 math prob 4, 12 math prob 4. That is not the right answer. That is definitely not the right answer. So how do I get the right answer? Make sure the denominator is in parentheses. So if we go ahead and do this, I don't really, oh, what just happened? I don't really have to close the parentheses if I don't want to, but might as well for posterity's sake. I get 91. Now, let's do this without a calculator. Now, you might look at it and say, well, 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 3 times 2 times 1. Now, normally you will not see me writing all this out like this. Okay, so, but this time, just for the first time, I actually am going to, and notice what happens here. I've got a 12 here, I got a 12 here, I got 11 here, 11 here, 10 here, 10 here, 9 here, 9 here, 8, 8, 7, 7, 6, 6, 5, 5, 4, 4, 3, 3, 2, 2, 1. Ones don't really matter if you want to cancel or not. And so notice all that I've got left here is basically this 14 times 13 over 2, and again times 1, but that doesn't really matter. And I could just do 14 divided by 2 is 7 times 13. Well, what do you know? It's 91. So I could have probably done that faster without a calculator than with a calculator. One of the things to recognize is instead of writing all that out, do you agree I could have written 14 times 13 times 12? Now, it just keeps on counting down. So right there, I'm just going to leave that at 12 factorial. And then on the bottom, I've got 2 times 1, well, whatever, that's just 2, times 12 factorial. And now I can go ahead and cancel those guys and get the same answer. So, just kind of recognize that if I wanted to, in any factorial that I'm taking, I could just once I want to, I can stop and just put an exclamation point there, and it just continues on counting down. And so notice I broke it up so that way I could stop. So I'd have a 12 factorial in the numerator and a 12 factorial in the denominator, and that made it nice and quick. So I don't really have to write all that stuff up. Okay, so n factorial times n minus 1 factorial. Again, that might look a little bit confusing right now, but remember n factorial, well, it's going to be n times one smaller, a number that's one smaller. So n minus 1, and then it's going to be n minus 2, etc. But like we just said in A, I can add an exclamation point, and that will carry it down to the end for me. So I get n times n minus 1 factorial over n minus 1 factorial. Notice what happens? I get n. Finally, C. Let's just do that one on our calculator. Oops, not times. Divided by 998 factorial. And, uh-oh, error overflow. That's too big of a number. Or the calculations involve too big of a number because our calculator is not very bright. However, if we come over here, we can see, oh, this is 1,000 times 999 times 998, and it keeps on going from there. And so I just break it up that way, and I get 999,000, which is a big number, but not so big our calculator shouldn't be able to handle it. But our calculator is not smart enough to do that. Our calculator tries to evaluate what 1,000 factorial is first, which is humongous. I cannot express how big of a number that is. That is thousands of order of magnitude bigger than the number of particles in the known universe. So that number is absolutely massive. Summation notation. So this right here is the Greek letter in the middle there is a capital sigma. So a lot of times it's called, usually I actually refer to it as sigma notation. And we represent the sum of the first n terms of a sequence by that symbol. So I is the index, n is the upper limit, or sometimes upper bound, lower limit of summation. Any letter can be used. Typically it's I, J, or K. Sometimes N, but N can make it a little confusing sometimes. And writing out the sum of summation notation is called expanding. So basically what this means is, looking at A, is I'm going to plug in 1. This I equals 1 is basically saying, what do I start for plugging in for I? And this 6 up here is saying, where do I stop? So I'm going to plug in 1, 2, 3, 4, 5, and 6 into that equation, and I'm going to add them all up. So I'm going to have 2 times 1 squared plus 2 times 2 squared plus 2 times 3 squared plus 2 times 4 squared plus 2 times 5 squared plus 2 times 6 squared. So to make it easier, these all have a 2, so I could just, you do it however you want, but I'm going to do 1 plus 4 is 5, plus 9 is 14, plus 16 is 30, 55, 61, 91. So I get 91 times 2, 182, I believe is my answer. Now I want you to be able to do this by hand, but you can use your calculator for this. It is possible to use your calculator for it, but you definitely need to know how to do it by hand. I'm actually more interested in you knowing the process than I am interested in you getting the answer. You'll use this quite a bit when you start talking about the integral in calculus, so it's useful to really have a thorough understanding of this. But let me show you how to use your calculator if you want to. You can go to math and then summation, and I'll just use X because it's the easiest button to hit. You could do I if you wanted to, but make sure you don't use the imaginary I. You just have to use the letter I. But I'm going to do X goes from 1 to 6 of 2x squared. So I just replace my i's by x's. And I do that, and I get 182. So I didn't make any mistakes with my math. So again, you can use that to check your work, but I really want you to know, I want you to be doing these by hand just to get it hammered in what's actually going on. So this one again, I'm going to plug in, I'm going to start at 3, and I'm going to go count up to 5. So it's going to be 2 to the 3rd minus 3 plus 2 to the 4th minus 3 plus 2 to the 5th minus 3. So I end up basically 8 minus 3 is 5. 16 minus 3 is 13, so I'm at 18. 2 to the 5th is 32 minus 3 is 29. So 18 plus 29, 47. So again, I could go math. Let's just check our answers. I'm going to say x goes from 3 to 5 of 2 to the x minus 3, and I get 47. Make that a little bit neater. Now the C looks a little bit weird. You might think, well, yeah, what even is this? Well, when I equals 1, what do I get? Well, I get 4. When I equals 2, what do I get? Well, I get 4. When I equals 3, what do I get? Well, I get 4. I just wrote a 3, but I meant 4. I equals 4, I get 4. I equals 5, I get a 4. So basically what this is saying is, again, this is I equals 1, 2, 3, 4, 5. And each time, when I since there is no I in there, our value of our function is 4. Another way to look at it is if we were to graph it, right? 1, 2, 3, 4. It's going to go, because y equals 4 is just a straight line. We're just going to add up 4 plus 4 plus 4 plus 4 plus 4. And I get 20 as my answer. All right. Now, let's look at D. See what we get? We get 1 squared plus 2 squared plus 3 squared plus 4 squared. So we get 1 plus 4 is 5, plus 9 is 14, plus 16 is 30. Now we plug in, so this one I'm going to get 0 plus 1 squared plus 1 plus 1 squared plus 2 plus 1 squared plus 3 plus 1 squared. Right, I'm plugging in 0 through 3 and adding them all up. Well, notice I get, that's just 1 squared plus 2 squared plus 3 squared plus 4 squared. Oh, so that's all 30 again. And finally, let's look at this one. We plug in 2 minus 1 squared. We plug in 3 minus 1 squared. Plug in 4 minus 1 squared. Plug in 5. Well, 2 minus 1 is 1 squared. 3 minus 1 is 2 squared. 4 minus 1 is 3 squared. 5 minus 1 is 4 squared. So I end up with 30 again. So it's just kind of nifty to see that really D, E, and F are exactly the same calculation, right? It's just this D, we go from 1 to 4, and our function is I squared. If you think about it, this I plus 1, that plus 1 in there, think back to chapter 2 in our transformations, right? That's basically shifting everything to the left 1. Well, what did we do with our indices, right? Our lower limit and our upper limit. We shifted everything left 1. And so by shifting our function to the left 1, but also shifting our which terms we were looking at, left 1, it doesn't really matter, we get the exact same answer. Same deal, except for F, it's shifting to the right 1. So again, if you compare right 1, 5 is 1 to the right of 4, 2 is 1 to the right of 1, and so we're really doing the exact same sequence. And sometimes that's a nice trick. Sometimes one of them is a lot easier to deal with than the others. All right, now let's go the other way. So if I want to express each sum using summation notation, this one, there's really not much I can really show you too much on this. It's I think if you have trouble with these, kind of keep practicing examples like number 5, and then when you get more comfortable with that, going backwards is a lot easier. Because if I look at this, the way I think of this is I've got my sigma I equals 1 to 9 of I squared. Because I look at the pattern, I see I have 1 squared plus 2 squared plus 3 squared plus all the way up through 9. So I'm going to start at 1, go to 9. each of them is squared, and then I'm going to add them up with the sigma sign symbol. So this one, do I notice anything? Well, this is 1, 1/2, 1/4, 1/8. Okay, and then it might have been a little bit harder, but it gives me kind of the nth term here. All right. If they didn't give me that, it's a little bit harder to look at. It's still something I would expect you to be able to do, but they give us that nth term. And so if I go I equals 1 to n of 1 over 2 to the n minus 1, we can plug things in and see how it works, right? So let's just check. Sorry, not 2 to the n minus 1, that's an I. That's my mistake. I minus 1. So when I equals 1, I get 1 over 2 to the 0, which is 1 over 1, which is 1. When I equals 2, I get 2 to the 1, which equals 1/2. When I equals 3, I get 3 minus 1 is 2, 2 squared, 1/4, and it looks good. I haven't proven anything, but I've shown that it works. Finally, here's a big wall of information, but basically what it is I'm just going to go through it really quickly. The properties of sums that we wish would be true are generally pretty much true. Now, notice we can multiply by a constant in number 1, and 2 we can add 2 sequences, and 3 we can subtract 2 sequences. But we cannot multiply 2 sequences together. It doesn't quite work that way, at least for infinite sums. So let's just look through number 1. If I have 1 to 4 of 3i squared, notice if I do the calculation straight up, this is what I get. But notice, what do all those terms have in common? I've got a 3 in each of them, so 3 times 1 squared plus 2 squared plus 3 squared plus 4 squared, which, so I can go from here to here, which is equal to the thing on the left side. So those are just kind of proofs. But basically, multiplying by a constant, adding or subtracting are okay. Multiplying and things like that, there are certain scenarios where we can, but just don't think that as a general rule that you can. We can multiply by a constant, you can add or subtract. And that's it for this video.